Okay, I think we can slowly start. Thank you very much for coming after this long week, coming on this lovely day. So this is the 6th edition of the Spinal Cord MRI workshop. Very brief overview of here. Okay. Very brief overview of those workshops for those who for whom this is the first time they come. So we have started this initiative in Milan in 2014. It was Paul Summers' main initiative to organize that. It was a big success. We had 30 to 40 attendees, and then it was an incentive to. You can see the screen on the. Okay. So what should I do?
Maybe his.
Should I reshare?
Reshare, yeah. Right.
Okay. Okay. I cannot share this often. Okay. So you see the desktop, right?
Yes.
I'm going to start the presentation again.
Yeah, that's perfect.
Yeah?
Yep.
Perfect, perfect. Good. So it was initiated in 2014, and since then we had a workshop every year, and we usually managed to do it right after ISMRM, because we know that the critical mass of smart brains are here around. So there was one in Toronto, Singapore, Hawaii. We had like a booth of attendees, obviously, for Hawaii, Paris, and then we started to diverge a little bit. And Ferran Prados organized a workshop in London this year, 2019 in January. So this is the first year that we actually have two spinal cord workshops, one in London, one in Montreal. And we're going to discuss at the end of this meeting what we can do next, what's best for the community. And if you're not on the mailing list yet, feel free to subscribe on the website www.spinalcordmri.org. So I want to mention that this is an interactive session, so feel free to interrupt me at any time. The goal is really to foster discussion. So the menu for today is to do a series of power pitch presentation from excellent speakers, and it's going to be 3 minutes for each presentation, followed by questions. So we'll try to keep it between 5 and 6 minutes per presenters. Then we are going to dive into the main topic of today's workshop, which is the results of the generic multi-center, multi-subject protocol. Part 1 will be the boring part, where I'm going to talk about mostly the experimental setup, the methodology, the processing, and so on. Then we're going to get some refreshments. Then we're going to go for the second part with the exciting, like the actual plots of the results. Then we're going to discuss what we can do next, ideas of topics, things that you would like to add to the agenda. And then a lunch. Any questions, suggestions so far for the agenda? Okay, so it's a great pleasure to have a series of great talks. We're going to start with Simon Levy, who's going to talk about perfusion, and then we have Rob Barry, Shiva Sharampur, Alan Zeifert, Adam Borak, Michela Patini, Yann Balosek, Benjamin Delanier, and Anna Combs. So, Simon, you want to come on the stage? So let's see. Hopefully the sharing thing will work seamlessly. All right. How is that looking? Very good. This is yeah.
Okay, good morning, everyone. Hope you had a great afternoon. I'm going to briefly summarize my talk I had on Monday about perfusion of the spinal cord. I hope you look at what will be like to qualify the perfusion in spinal cord? Because as most of you might know, perfusion is essential to tissue life, and it's even more important in spinal cord cases because it is at the root of the chain of events of these injuries. And it's even more important because the compression surgery procedures are sometimes not trivial. And so we would like to provide a biomarker more directly related to the tissue viability to those conditions, procedures. So how to measure human spinal cord microperfusion in vivo? So we have several challenges to tackle. The perfusion we expect within the spinal cord are very low. We also expect a similar higher microperfusion levels of the gray matter compared to the white matter. As most of you might know, there are additional sources compared to the brain, as visceral variations or syncytosis and complex movements. We also need a very high resolution to access, for example, the microperfusion levels of the gray matter. So given the great achievement of diffusion, we went for the intravascular motion technique, IVM, which aims at quantifying the signal decrease at low p-values, supposedly induced by blood water circulation within a randomly oriented capillary network. We use this representation of the signal at it's the microvascular volume fraction, this is the microperfusion rate coefficient, and the diffusion coefficient of water within tissue, as you probably all know. So we first optimize an acquisition protocol at 7T for maximizing the SNR. We applied it to 6 healthy volunteers. We aim for a resolution of 0.77 square millimeter in plane. We aim for a very short TE. We require 16 value, 30 repetitions per value in this in 3 orthogonal directions. We also synchronize the acquisition with the similar and we split the acquisition in 2 phase directions to further correct the distortions. On the other hand, we also assess the estimation error of the pitching procedure for a given SNR using Monte Carlo simulation to simulate perfect data, you add some noise, and then applying the fitting algorithm, you can map the estimation error on each parameter for a given SNR. Pushing those simulations, you can also determine the minimum required SNR to estimate the parameters for good accuracy. So you see that those parameters are quite high. Looking sugar is here. Here are the results of the in vivo IBM maps. So you see that for one slice, in one subject, it's quite difficult to discriminate the gray matter from the white matter. But when we average our 6 slices, we start to see the higher microperfusion level of gray matter appearing here. We have L star and here. And when we average across our 6 subjects, we are getting more defined maps with the higher level of perfusion we expect for gray matter compared to white matter. So just to finish, so this is the first study to map the spinal macroperfusion in vivo, relating our simulations to our in vivo work. We have an error in average of 13% on an individual basis. Of course, we're still far from clinical constraints, so it's is too long, and the maps are not reliable on the single cell basis, but there's still room for improvement, like we could investigate these patient approaches and optimize, for example, the number of p-values plus number of repetitions of p-value that has been appropriate on this study. So thank you for the attention.
Great. Floor is open for questions.
Really nice work. One question, also treatment in motion compensated ratings, maybe erase the effect of IBIM to get like a contrast specific to.
So we tried the motion capacity gradient, and indeed it's raised the IBIM effect. So these were monotone gradients. So there's no motion compensation, but it worked for motion in the post-processing. Yeah.
Is it clinically relevant to distinguish between gray and white matter, or can a yellow confusion occur in each patient?
Yeah, that's a good question. So what we would like is to have a map of the perfusion within the spinal cord. So indeed, maybe just one measure by slice or by level would be relevant for the clinicians, but the idea is to like we also have projects to relate those level of perfusion with the compression, mechanical compressions, because you have, for example, in scoliosis, they add some implants to get the vertebral column more straight, and sometimes it pushes the spinal cord, and we would like to know, for example, if one part of the spinal cord is affected by this implant which pushes the spinal cord. If we can push more, or we have to push less to not to decrease the spinal cord, the perfusion level.
So maybe I have a question in terms of how to tackle the highly noisy maps. So you mentioned like Bayesian approaches, which would be more on the processing side, right? Do you think that would really address the high level of noise that we're seeing on those maps?
That's a good question. I think we tried. So Bayesian approaches have been shown to be more robust to noise, but it had some details sometimes. Or there's also deep learning feeding approaches that have been developed. I'm not sure that the error we have here is only due to the feeding approach. I think there is also modeling things. Also, maybe there are some questions about the CSF within the interstitial space, which could add some values, some IBM effect. And we can also correct for the T2 of the blood, which would lower the values of IBM. Yeah, that's been done.
Okay, so let's thank our speaker here. Yes, next one. Avec ça, next speaker is Rob. Is Rob here? Because I think he's just writing. So maybe we can give him a bit of time. Shiva, you wanna go? The next. so it's on va voir si maybe you can try to speak and see whether
I think it's.
yeah, the room is not that big. So, all right, so next speaker, next speaker will be Shiva Sharanpur from Temple University, Thomas Jefferson University in Philadelphia, going to talk about pediatric spinal cord complaints.
Good morning, everyone. So today I'm going to talk about the development of a standardized normative pediatric spinal cord template. Okay. So when we need template at all, so we know that templates in and specific spinal cord templates, they provide a normative reference for structural and functional measurements, and they also help us in making, actually helping us in the goal of improving the accuracy in the diagnosis of the spinal cord diseases, and how effective are the treatments throughout the longitudinal studies. So a little bit up on the background here, you can see the other templates that were created before with the previous groups, but as you can see, most of them are only covering the cervical spine. In this slide, on the left side, you can see the PAM 50 template that were created by the Norfolk group, and it had the 50 adult subjects and 61 CT contrast. On the right side, you can see our pediatric template. I'm going to talk about this more on the next slide. So for our template, we actually recruited 30 healthy pediatric subjects, and the age range of our group are 6 to 16 years old. The scans were taken with space sequence with a 3 Tesla Xenon scanner, and the scans were acquired in 2 different slabs. They were stitched together to cover the entire cord. No need to say, we used the spinal cord toolbox to create our template, and there were quite a few of pre-processing steps that we have to go through, like spinal cord segmentation, center line extraction, and we had to straighten the spinal cord and then the vertebral lever align, so we could finally run the nonlinear shredded deformation to register our T2 images into the template space. So to show one of the application of our template, we also measured the cross-sectional area across all the levels of all the 30 subjects that we use in our template, and compare that measurement with the generated template. Here again is the template. From left to right is the sagittal coronal labeled, segmented, and I can't point to this, but this column is showing the probabilistic map of white and gray matter, and the last column is the segmented cord and CSF. So here you can see the basically this graph is showing the cross-sectional area measurement for the generated template. The average across the levels is 46.5 millimeters squared. We compare that value with the equivalent of the measurement that we run on all the 30 subjects. The average for the 30 subjects is 47 millimeters squared. So this suggests that the spinal cord cross-sectional area is basically preserved between the native subjects space and the templates. And here again is a summary of the comparison between the measurements that we ran within the templates and all the subjects, and to make sure that our data is reproducible and how close our measurements are between these two groups. We also computed the ICC, which turned out to be 94%. And in conclusion, so we believe this is the first pediatric spinal cord. It's only in structural. This is very primary data, so there is a lot of work to be done in future. And like obviously we have to recruit more subjects. We would like to categorize based on the age and possibly the gender. And there's so many other things like extracting the white matter tracks, and I'm actually using the VTI data on our subjects, on our template. And that's pretty much it. Thank you. Yes.
Do you plan to work on the template for stabilizing in France?
For silent.
If you plan to make in the future template for stabilizing in France?
In France, we actually do not have that population, unfortunately. Like I said, it's only 16 years old. Yeah, but I believe I saw some group, they were working in London, I don't remember exactly, but they were working on impact. It's pretty challenging, so I look forward to it. Yes.
Are there many significant morphological changes in software movements? Or
Even in our population, I can say this is a very growing population. So some of our subjects are very tall, some of them are shorter. So yes, there's a large variation that we need to address that in future by improving our mechanism of creating the template. Yes, but definitely for impacts, I believe it would be even more significant.
Have you tested this template in pediatric patients with some spinal cord injury?
That's a good question. We also have a spinal cord injured population. That's the next step. We're going to use those subjects to be that integrated to our template.
Do you know the disease they have?
They usually have acute injury. So, but yeah, that's the population we already have their scans. So we
because I have 20 patients with Friedreich ataxia. They have around from 10 to 16 years old.
Okay.
So maybe we can share. I can share.
Yeah, definitely. That would be it.
I think it would be great for you.
Yeah.
Thank you.
Thank you.
All right. Thank you very much.
Rob with us.
Alex, is it good?
Ouais.
Excellent. So it's a great pleasure to have Rob Berry from MGH talking about practical protocols for measurements of resting state functional activity.
Great. Thank you very much, Julian. Good morning, everyone. So Julian asked me to give a talk, and to be totally honest, I wasn't too sure what to talk about. We've been involved in a few things in the last year or two, so it's some exciting work. But I wanted to talk just for a couple of minutes about this project. So in case you don't know me, I did some work a few years ago looking at functional connectivity in the spinal cord at 7 speed. And this was a lot of fun work, and we recently translated this to study functional networks in patients with relapsing remitting multiple sclerosis. I just want to give a big shout out to Ben Conrad for this paper. He took it across the finish line. And Ben was actually so kind of inspired by the scientific process. He actually resigned his RA position and became a PhD student. He's now half done his PhD as a result of this work. So we're all very proud of him. So the top two questions that I've gotten in the last couple of years is, why don't I do this work at 3 Tesla? And why don't I use the spinal cord toolbox? These are questions from all the anonymous reviewers, some of which perhaps are in this room. So I'm working on the second one. I recently started using it for my work. So I want to talk for the next couple minutes about the first question, about why don't I do work at 3 Tesla, and what can perhaps be done at a field strength at 3 Tesla. And just my own defense, I actually started my work at 4 Tesla, and I went up to 7. So now I'm kind of aliasing and going back down to 3. So that's just what I'm doing here. So this paper came out, actually, Steph and I published it just a few weeks ago. So if anyone doesn't care about functional imaging, this was actually had nothing to do with fMRI. It's all relaxometry in the spinal cord at 3T. Not with the spinal cord toolbox, but you know, all the data, I think we can make it available to anyone who does relaxometry. They take a look at things like the white matter tracks, etc. So I decided to share for the next couple of minutes some of the work that I did at 3T. So basically, I translated the functional protocols that were implemented at 70 down to 3T. So on the Philips system, this is a highly multi-shot fast field echo, what Philips says. So lots of lines of, lots of acquisitions and excitations, and it's 3D volume excitation. So we basically just copied and pasted the protocol down to 3T to continue the work. And in the brain, a lot of people have spent time looking at effects of TE, effects of bandwidth, what happens if you keep the person in there for 4 extra minutes. These are all considerations in the brain in fMRI. And so I decided to try to look at some of these things in the spinal cord. To the best of my knowledge, no one's ever really looked at this yet. So for example, the next couple slides just showing some of the effects of TE. So in the first column here, you have the high resolution anatomical, which is a combination of 3 or 4 echoes, as I recall. And then the next 3 columns is actually having 3 different functional runs with different TEs. Now, of course, TE influences the functional contrast, but also influences the spatial contrast and the spatial artifacts, which will then, of course, influence your registration algorithms. So this was kind of interesting to see. So with regards to robust implementation of algorithms to do with functional anatomical registration and alignment, you have to consider the fact that these artifacts may actually depend upon the echo time that you use for the study. Also, in 3 subjects, we were taking a look at the networks and whether or not there's some sort of linear dependence. And unfortunately, there's not a lot I can kind of say here in terms of strong conclusions. But these data were acquired right before I left Vanderbilt, literally like a couple days. I should have been at home packing, but I was actually at the scanner collecting these data. So some interesting stuff here, and definitely suggest that other people, there's an opportunity here to take a look at TE dependence for the functional network, try to do some stuff in that realm. As well, we were taking a look at how long to scan, kind of leave the person in there for a good 20 minutes and see that they don't fall asleep. What can you see in terms of these resting state networks? So here's an idea of kind of take a look at 2 to 20 minutes in intervals of 2 minutes, what happens to these networks. And this actually is following some of the stuff in the brain, taking a look at the stability of these networks. They kind of appear around 6 minutes, maybe become stable around 8 to 10, and sort of steady state appears to be after about 10 to 12 minutes. So finally, we were taking a look at the effects of bandwidth. So lots of interest recently in the fMRI literature, taking a look at, what about, things above your canonical 0.1 hertz. What happens if you keep those high frequencies? What happens? It's always in the signal. Who knows? Let's talk about it. So this is one of the discussions about the influence, and actually taking a look at run length doesn't have a major effect, but actually how you filter your data has a tremendous impact. So that was a very interesting thing to learn about. So all of this and more is in this paper here, so please feel free to read it, ask if you have any questions. The discussion section is quite long and rambling, talks about many of the things that I observed, and future considerations for people that are setting up the protocols for functional imaging of the spinal cord. So all this work has been done over the last few years. I'd like to thank all of my colleagues and friends and sources of funding from the NIH. And also just want to put a quick bug in your ear that in the next few weeks, there's a very strong possibility that there will be a posting for a position in my lab to continue doing functional imaging at 70. So please stay tuned to the Twitterverse and the Spinal Cord Workshop forum and for that posting. Thank you for your attention.
I guess I'll start working the eye. So I wasn't one of the reviewers.
You were?
No, I was not. But I had like I would add like a third point here, because talking to people about functional connectivity, and also have the same concern is obviously the potential effect of like the physiological variation and vascular flow and motion that is present in the spinal cord that contributes to the variance of the signal. The typical answer is that there is special filtering, and you actually say that filtering is very important to basically focus on the spectrum that we think is more related to the bold functional connectivity. But we could also argue that maybe there is still some physiological component in that spectrum. So my question would be, how do you view this potential confound and address it?
Oh, absolutely. Yeah, no, that's really important, because if you see something, that doesn't mean it's a functional network. It just means you see something that's temporally correlated in time. So I think to address that head on, we have to take a look at some metric or metrics of the general reproducibility of the work. I would like to think that for many of the physiological properties, although they're correlated in time, if you were to do the same scan, twice or 3 times on the same person, they probably tend to be incoherent across time. Whereas the networks that are genuine and represent something related to the underlying physiology, I would say that they tend to be more reproducible. So that was the approach that I was trying to take to address this. If you see something correlated, you can't prove by example, but you can disprove by counter example. So I was definitely trying to address that by looking at the general reproducibility in terms of interclass correlation coefficient. We also did a little bit of work in terms of changing the acquisition parameters and having a 20-minute run length to see, like, if you change the parameters, you get roughly the same network appear, and we thought it seemed to be reasonable. There's definitely a lot more that I could do. I could go back in time, like 3 or 4 years when I was acquiring this data. There's definitely a few more ideas I have now that would have influenced this work. But it's definitely an open question. And I think that as a community, there's always been people saying, oh, it's just motion. Oh, it's just physiological. And it's like, it's a possibility that we have to kind of address intelligibly and have some good discussions just to kind of confirm that what we're discovering is meaningful and reproducibility, not only within the single subject, but also across labs. I certainly hope that the stuff that like Alan is seeing is stuff that I'm seeing as well. And I
want. How many functional approach do you take? Just only one, or several, and they are varying, for example, over 6 months?
Yeah, so what we've observed, and this has been observed by myself and other groups who've been doing this work for the last few years, is there seems to be 2 different networks. There seems to be a ventral network, bilateral ventral network, and a bilateral dorsal network. And people have looked at connections between ventral and dorsal, both ipsilateral and contralateral, so all different permutations. There's not a lot of evidence building up for any other networks. A couple of people, like the UK group, have also looked at kind of connectivity along the cord as of I. And there's the correlations along the cord actually seem to drop off quite considerably after about 1 vertebral level. So it seems like the most reproducible and significant correlations tend to be like within an axial slice and bilateral, motor, and sensory. But as I described in this paper, the sensory networks in the dorsal horn connectivity, they seem to be a bit more elusive. I can't quite put my finger on it. I think a lot more discussion and work is needed to figure that out. The size of the ventral horns are different. Maybe there's a bit more just susceptible to distortions. Maybe this is something where the spinal cord too will use to investigate it as well. So it's something that I'm not totally, I guess, satisfied with some of the stuff today. It's still not converging. You talked with Falk about this, and the ventral network seems to be converging. Everyone seems to be reproducing it. The dorsal seems to be a bit more elusive. So we need to look at that.
Good. Right. That's thanks for the speaker again.
Next will be okay, right here.
Good. So Alan Seifert from Montreal, and it's going to talk about fMRI of the spinal cord at 70.
All right, thank you. So 70 provides us the higher SNR and increased fold signal that we need to do functional MRIs on the spinal cord. But because of the challenges that come with the shift to 70, there's really a lack of consensus on the optimal fMRI acquisition protocol. You've really only seen a few 70 spinal cord MRI results in the literature. They were basically rocks resting state studies. So our goals here are to present our preliminary motor task fMRI results at 70 and to compare the results we got with single shot and multi-shot EPI acquisitions at a couple of different resolutions.
So these were the three protocols we tested. There was a single shot and a 4-shot EPI at 0.75 millimeter, and another 4-shot at 0.6 millimeter. And the task that we investigated was to tap the 3 fingers of the left hand rather forcefully against the thumb, and we expect this task to produce motor activation primarily at the C6 and C7 vertebral levels. So we motion corrected, straightened, and smoothed the time series data using a combination of FSL and spinal cord toolbox. Produced a 37-turn physio noise model and ran the GLM analysis in feet. And I'll go through these protocol by protocol. So here we have the activation and the TSNR maps for the single shot protocol. You see the TSNR really falls off significantly in the lower slices due to 4B1 and proximity to the lungs, those temporally varying field fluctuations. But we do see hand motor activation at C6. We see hand sensory activation at C5, along with some accidental, unwanted arm and shoulder motor activation. We see some other scattered activation, most of which we expect is false positive, but this looks a little bit reminiscent of those bilateral ventral networks that we saw in Rob's work. And here we have the signal and the model strip plotted over time in this most significantly activated voxel here in the green crosshairs. We see a bold percent signal change of just under 2%. So moving on to the 4-shot 0.75 millimeter protocol, we see the TSNR is higher and more consistent throughout the cord, but we only see this one activated voxel above this threshold that we've set. But fortunately, it's exactly where we expected given the task. So the bold percent signal change here was 1.8%, but the TE in this protocol was shorter than the TE in the single shot protocol. So this would produce some lower, a slightly lower percent signal change. So finally, we have the 4-shot 0.6 millimeter protocol. The TSNR is lower, as we would expect with smaller voxels. And we do see hand motor activation where we'd expect it, and this voxel up here could also be due to some unintentional arm movements. And we see a higher bold percent signal change of nearly 2.3%. So going through these numerically, we found higher Z statistics in the single shot protocol, higher TSNR in the multi-shot protocol compared to single shots at the same resolution. And we see the largest bold percent signal change in the multi-shot 0.6 millimeter protocol, which we believe is due to the longer echo time than the 4-shot 0.75 millimeter protocol, and due to less partial volume than the single shot protocol. So our preliminary conclusions here are that the multi-shot EPI protocol is slightly less sensitive to activation, but these activation maps are more consistent, and the images are dramatically less susceptible to distortion and signal loss. So thanks, I'll take questions.
How did you model the modeling response function for models you use? And modeling response function usually derives from visual cortex of the brain, and that's maybe more general question, but does exist some study which is verifying the brain-derived modeling response function corresponds to the modeling response?
Right, so yeah, I didn't do anything specific to the spinal cord here. We used the basically just the default, canonical HRF, basically just the default set of feet. So this is something that I'm interested in, figuring out how it's different or coming up with an HRF that's more specific to the spinal cord. But no, for this work, we just used the very, very default HRF.
So until now, there is any study verified?
Sorry?
So until now doesn't exist any study verified.
I'm not aware of one.
So what is the between subject variance
this was actually only one subject. So yeah, we're still working on getting more subjects. So yeah, that would definitely be the most valuable piece of information. Yeah. Based on what I've seen from thermal stimulus task fMRI in the spinal cord, the locations and the Bolder sensitive changes seem to be very consistent. We are probably going to switch to that. These motor tasks, this depends very, very strongly on how well the subject performs the task. So I've tried a few different subjects with this motor task, and they are very different, but they're much more consistent in a more standardized sensory task.
Maybe just to follow up on René's question, there is some work on electrophysiology where they use the pressure probe to measure oxygen changes with respect to measure the neurovascular coupling. And there are some comparisons between the spinal cord and the brain, notably showing that the neurovascular coupling in the cord is a bit faster than the brain. But yeah, I forgot the references, but there is work by Leblanc and Pichet who actually showed that and reviewed the literature of those questions. Yeah.
And also, I actually just a few months ago heard that Henry Gary an abstract that they dynamic response to spinal cord. Although actually still I just do a list of trying to find that one. I don't know if it's here, but I was told that there's abstract somewhere from
That was Leblanc and Glover.
So yeah, they are not in the same lab, but
In two different works.
Yeah.
Okay.
So I had a question. So first of all, in terms of like you mentioned about sensitivity, but so for example, the activation that we see on the first shot is, does not appear on the single shot. So do you think that this is due to like issues with the distortions and the signal dropout, things like that?
I would be more inclined to blame inconsistent performance of the task on this. Yeah, so I think if perhaps this one is a little bit better in avoiding arm and shoulder motion, and I mean there probably is a component of what you mentioned too. Here we're really starting to see a lot of the signal loss.
It's right at the level of the disc.
Yeah, and here that's preserved. So yeah, I think it's a combination of the two. The reason we don't see it here and we do see it here is probably you're getting more signal in the forejoint. And the reason that we do see all this up here but don't see it here, I think that might be, this was performed after the single shot, so I think maybe just might be practice of that, getting a little bit better at avoiding that.
And so I have a question also in terms of protocol optimization, and it's always been a debate also for the brain fMRI community as to, should we just get, smaller voxel at the acquisition part, and then in the processing, using filtering or all the other way around. Because obviously, by trying to get a better effective resolution, you also, we can need like larger matrix size, there is more distortions. And on the other hand, having 6 slices also introduce more intravoxel homogeneity and signal dropout. So I'm just wondering what's your take on, maybe using a bigger voxel but not doing filtering at the end.
Yeah, that may be something worth doing. I think we probably still want to smooth pretty dramatically in Z.
Sorry, when I meant filtering, I meant smoothing.
Oh, okay. Yeah. So I think we're going to need to get strike that balance between thick enough slices that we're getting enough signal and not so thick that we wind a lot of phase, lots of voxel and lose the signal. And I think my feeling is the best width for the smoothing kernel in plane would be about the same as voxel size, so probably about 0.75 to 1 millimeter in the XY dimension. So I've used bigger than that in this work. I want to look at smaller dimension. But I think still definitely a very large kernel in the Z dimension across at least a couple of slices, just to try to these effects are spread rather in a rather large extent in Z, the activations. Probably thicker than in the slide, so I want to sort of mute.
Excellent. Well, thank you. Thank you.
About that for several hours, so we all right, the next one will be Adam Dvorak. Dvorak, right? That's the right pronunciation.
Yeah.
Okay. Adam is going to talk about what's new in spinal cord imaging at UBC.
All right, so I'm actually going to give a really quick overview of 3 related projects we've done in roughly the past year at UBC. So the first project is the first application of the Grays sequence for rapid myelin water imaging in the spinal cord of patient groups. So we also acquired diffusion tensor imaging and quantitative T1 for comparison. And we acquired this data in 2 primary lateral sclerosis patients, 2 MS, and 2 NMO. We looked at ROI results, but it's a lot prettier to look at Z-score maps, which we also produced. And they showed good agreement between the different quantitative metrics. And an especially interesting thing that we found was congruence between low myelin water fraction in the Z-score map and lesions in a primary progressive MS patient, and then also a longitudinally extensive transverse myelitis lesion in an NMO patient. Our second study that I'll mention is creation of a multivariate myelin water atlas. So we submitted this ISMRM abstract with just the brain, but then we also added spinal cord data. So it's 28 subjects, and we were doing this to compare traditional multi-echo techniques for myelin water imaging, again with the Grays sequence, and compare that to a variable flip angle steady state approach with the McDesbot sequence. So we co-register all subjects' images simultaneously, and that produced our multivariate templates, and then our myelin water fraction atlas for Grays. So that's the traditional multi-echo approach. Looked really nice. It had great contrast between white and gray matter, and even within white matter, which you can especially see in the dorsal column. And the McDesbot maps looked a little bit less nice and had surprisingly low myelin water fraction. And this was because we tried to match our analysis parameters between brain and spinal cord, and the parameters that work well for brain are definitely not appropriate for spinal cord. Then we looked at our results in the context of patient pathology. So here's a representative relapse and remitting MS patient with a low level of disability, and we see very little deficient myelin water fraction. But if we look at a primary progressive MS patient with a high level of disability and also lesions throughout the imaging field of view, we can see very clear evidence of pathology and reasonably good agreement between the 2 techniques, although they're definitely different in some regions. Our last study that I'll mention is actually imaging the PLS patients that were in the first study again. We were surprised by how much evidence of pathology we found. They were almost like a patient control group within that study. And so we wanted to do follow-up imaging because previous studies have found that PLS patients show really clear longitudinal degeneration, whereas a similar disease, ALS, does not. So we used a spatiotemporal normalization technique, which basically creates a patient-specific template where you can look for changes in quantitative metrics with really high anatomical alignment. And we looked at our quantitative maps from the 2 visits for both patients. So the follow-up visits were 10 months after and 11 months after for the 2 PLS patients. And we saw reduced fractional anisotropy, increased mean diffusivity, and reduced myelin water fraction. And all 3 of these have been found previously in motor tracts in PLS brain. So this was pretty interesting to see. And lastly, we also created longitudinal Z-square maps. So these are Z-square maps not of an individual time point, but actually of the change in quantitative metrics in just under a year. And these reiterate the trends we could see more qualitatively on the previous slide. And I think it's especially interesting to point out that the fractional anisotropy reduction seems quite focal to the lateral motor tracts, especially for the first PLS patients. So the first project was just accepted for publication, and I presented the other two at ISMRM. But feel free to contact me if you'd like to know more about any of these studies.
So usually much more here. There's homogeneity in spinal cord. So the teachings are how much of the condition right now is phase. How much better these rates and these big comparable.
So it is because the main improvement we have with using the gray sequence and adding those 2 extra gradient readouts is really just with time. So we have roughly a third of the acquisition time. The difference between the spin echo sequence and the gray sequence, I think, is qualitatively very similar to brain. The myelin water fraction results are extremely similar. We have a paper that's in preparation right now, doing a direct comparison of the two. But yeah, I think that it works quite well. We've tried higher Gray's factors as well, Gray's factors of 5, and had no luck with that. So right now we're sticking with that sequence.
Sorry, you probably mentioned it. How long was the protocol for the multi-echo grays in this course?
It's 8.5 minutes, although this was on our 15-year-old scanner, and so on the new scanner we just had installed this past fall. I think we should be able to push that quite a lot faster, or acquire in the same amount of time, but get coverage of the whole cervical cord. So right now this was centered at C2, C3, and covered about 3 vertebral segments over 50 meters.
All right, thank you very much.
Next speaker will be Michela Platini. Sorry, I probably mispronounced your name. Michaela, okay. Dr. Platini from Santa Lucia in Rome, going to talk about standardization of pipeline for fMRI in the spinal cord.
Thank you. So this is a work and collaboration with the Quantitative Santa Lucia, that is an hospital in Rome, and the Institute of Lipotherapy Center, and also we collaborate with the spinal cord networks. Thanks. So, which is the aim of this project? This is some results obtained with fMRI. So it's a promising tool for non-invasive assessment of human spinal cord function following traumatic injury or neuroplasticity. But instead of, it is essentially explored in clinical setting due to several challenges probably related to images acquisition and analysis that as we see before in the previous year. So it needs an optimized spinal cord fMRI, experimental data analysis protocol, and also another problem is to characterize well the biophysical feature of the spinal ball functional response. In this program, we try to develop and increase sequence and analysis pipeline to increase PPM SNR to remove the physiological knowledge. And also we try to understand better the biological feature about both spinal cord by studying the relationship between the stimulation, strength, and the functional response by performing a spinal MRI isometric motor task. So the first step that we did is to improve the technical condition to provide the best MRI imaging quality. Because the first step we think that is to have the best experimental approach. So for this reason, we acquire the images in a digital and axial direction, and then we compare the scenarios. Also, we acquired 48 subjects, healthy subjects, and 48 multiple sclerosis patients in the prechronic state. And we perform a symmetrical task force. Then, thanks to this, we develop and improve and develop a spinal cord MRI analysis pattern based on spinal cord tools. And thanks to this, we obtain that we increase the TSNR respected to the arithmetic we were driving of about 41% in the axial view, and in sagittal about 20%. In addition, we have good results in the fact that the activation is inter-subject increase. Also, we obtain thanks also the co-registration with the funds template, it could be possible to have a high inter-statistical inferences. And also, we compare the control subject with the patient. This is the preliminary results because we have to increase the number of patients because here is only 40 and the control subject is 46. That we have obtained an increase of intensity of functional signal in the patients respective to the control subject. And we think also that narrow this subject type that is due by rearrangement of the motor task. So we can conclude that we implement a optimized spinal cord MRI data analysis pipeline built around the spinal cord toolbox, and we acquire actual and significant functional images at 3 clusters from the spinal cord of 46 subjects and MSF patients. And using our spinal cord based pipeline, we substantially improve motion correction, which is the main result that we obtain, and the image registration. Furthermore, we found testing use activation with a high level of statistical signal. So thank you, and also thank you to my colleague for more.
Thank you very much. I just missed it, but what was the improvement you saw relative to 3D warp drive?
Yeah, because we analyze in the data with the spinal cord toolbox pipeline, the tower and with that. And in particular, we observe that respected to we have the
labels are really small. Which one is 3D warp drive?
Where this is the digital view before and after.
Okay.
And this is sorry, this is and also this is axial after and before. So we increase the inter-subjects, the TSNR. In the axial view, the 7%, because we calculate the coefficient of variation of TSNR. And we observe that inter-subject with this kind of pipeline, we increase of about 17%.
So for 3D warp drive and for the other motion correction algorithms, do you have a mask? Because you have to like kind of focus the.
Yeah, for the 3D acne, yes. For the spinal cord toolbox, we try with and without the mask. And we observe that we have not activation outside of the spinal cord. because this is the point. Because with the mask, we can remove the signal for the external part. We don't consider it.
What was the scan time again? What was the compliance?
Sorry?
The compliance of the clinicians. So what's the scan time?
The scan time, so they perform 4 runs of about each run is 5 minutes. But they are 5 minutes of run and then they rest and then 5 minutes because for some patients it is so hard to stay more inside. So more or less all the task is about 20 minutes in the scan, not all. Plus the 10 minutes, in general 30 minutes because we have also the clinical sequences that have to perform.
All right.
Okay.
Actually, we have one question.
Sorry, from the disembodied voice.
Yes, George Patrick, Cardiff.
I was just going to ask, as part of your pipeline, did you have any independent component analysis cleaning of the data?
Yeah, sorry?
Did you use independent component analysis at all to clean your data before you analyzed it?
No, we don't use in clinical data.
Some ICA independent component analysis for removing physiological noise.
Yeah, is there a try?
The retroic or.
I must have missed it. Sorry.
Yeah.
Okay, for the PNM. Okay. Yeah.
We improve the pipeline and then we put all the best program that we can extract the best information.
Fine. Okay. Thanks.
So thank you very much. Right. The next speaker is Untitled. There, so Untitled from Czech Republic, University Hospital Olomouc, who's going to talk about cone-specific microstructural changes in patients with asymptomatic cord compression.
Good morning. Thank you for the introduction. Our research is focused on asymptomatic patient with cerebrospinal cord compression without any clinical signs or symptoms of myelopathy. So the aim of this study was to find a marker of the yearly microstructure damage of the compressed cerebrospinal cord in this patient. So we acquired 67 patients with non-myelopathic degenerative cerebrospinal cord compression and 29 healthy controls. We scanned data at 3D Siemens plasma, and our protocol consisted from the star-rated structure image and from the optimized highly illuminated diffusion protocol with 63 direction on 3D values. Analysis was performed using the FSL and spinal cord toolbox libraries. We estimated 2 diffusion models, DTI and ball and sticks. For the DTI, we derived 4 microstructure parameters: fractional entropy, mean diffusibility, axial diffusibility, radial diffusibility. And for the second diffusion model, for the ball and sticks, we derived mean of diffusibility distribution parameter and primary partial volume fraction. And we then did the registration of the white matter spinal cord atlas to our anatomical space and define our radial interest for the 3 major white matter columns. And our results, we detected a statistically significant decrease of SPR and mean diffusivity for the ventral columns, and primary partial volume fraction derived from ball and stick model for the lateral columns in the group of patients compared to healthy controls. When we did more selective analysis in the level of individual interventional risk, we found out that these changes arise mostly from the segments C4-5 and C5-3. These areas are also mostly corrupted by compression, by maximal compressed level. We then did a correlation of the statistical significant diffusion metric with the anatomical measurement, with cross-section area and compression ratio. And we reviewed the following statistically significant positively correlated correlations. And finally, we compared the patient with abnormality findings in electrophysiological measurement. Again, the patient without any abnormalities in electrophysiological measurement. And we found out the statistically significant difference between these two subgroups of patients for the F1 for lateral columns. So this question the low values of axial and diffusivity in lateral columns and primary partial volume fraction in lateral columns point to external injury. This conclusion corroborates with finding in previous study. Also, we did not confirm the standardization, which was suggested as explanation for lower values of fraction and agitation. Diffusion alternation in lateral columns were more common in these patients who had already pathological findings in motor evoked potentials, and diffusion alternation correlated with the degree of spinal cord compression. So conclusion, optimized hardware protocol allows the current diffusion data in with excellent spatial resolution and clinical feasible execution time without significant corruption by susceptibility artifacts. And detected microstructure changes could be used in the future as potential predictor of manifestation of degenerative cerebral myelopathy. Thank you for your attention.
Did you observe any effects of laterality in the left and right?
In the left and right lateral columns?
And in correlation with the degree of compression?
We used one ROI for both lateral columns, so we did not.
We used the left and right part because some patients that have compression on the left side, some on the right side, so it's inconsistent in those patients. We would do a solution analysis for left or right, so that we do statistical solution. Let's patients on the left side and
yeah, it's right. So we did not do this laterality analysis.
I mean, thank you very much. I mean, the correlation with the degree of deformity of the spinal cord. If you observe the deformity is strong on the left side in one patient and in the right side it is not so strong.
We have these anatomical measurements which give information about the compression and so on, but we have numbers for cross-section areas and compression ratio, but from these numbers I do not see if for the first group when the compression is, if it's from the left or right side. So we didn't do this analysis. But thank you. Good stuff. I'm not sure if I heard correctly how we recruited the patient. Yeah, these patients underwent the neurological assessment and they do not have any myelopathic symptoms like weakness, numbness. They have full score and modified the Japanese orthopedic scale. So they have only the compression, and some of these patients have abnormalities in electrophysiological measurements. Yeah, in this case.
Yeah, they underwent detailed neurological assessment, and also they had MRI scans. They have no deeper signs of myelin.
Thank you very much.
Yes, gentleman Devinaire. Going to talk about setbacks.
Hello. So this is not a presentation that I made for SMRM. This is just quite like a really short study that I made on setbacks. And in the way of presenting at ISMRM, I have to say that I have no shares in that company, whatever the result will be. So if you have seen in the presentation, I'm really happy that more people are doing MRI now. And if you look at Rob Berry's presentation, it seems that functional MRI is really easy and you get beautiful images. But in reality, you often get terrible results if you don't take care of things. For example, if you see here, we use a ball, classical ball sequence, and you see signal dropout in the cervical area, and you see a little bit of gusting effects. And when we started doing functional MRI, we put a lot of effort into trying to get good imaging, and a lot of that was about patient positioning. And you see in the video that we even translated in Chinese, how to put patients to have a good positioning, having a straight spinal cord, and so that the shielding is done properly. And we also try to use these SATPAs, that is this backed field of liquids and gel that is supposed to improve the signal quality by reducing the susceptibility artifact due to the interface between the hair and the tissues. The company also says that it's going to improve the motion, so reduce the motion in the. So we wanted to evaluate that quantitatively, and we acquired 3 bolt signals from 3 healthy subjects that really are increasing to 10 now. But we also wanted to see what were the effect of these SATPAs on quantitative MRI. So we used this spinal cord generic protocol that you will see the results after to quantify what's the impact of these SATPAs on that. And we use the classical CT approach with restitution to template, evaluating in different regions, but I'm only presenting part of that. So overall, the functional MRI signals that these are resting states, we have seen that in the cervical region, we increased the signal intensity by approximately 200%, but also increased the TSNR by 200% in that region. And you can see, you can appreciate the improvement in the quality of the functional MRI just using the SATPAs. It makes sense because in that signal dropout, due to the susceptibility artifacts in the lower signal, we just increase that. We haven't evaluated the effects on the connectivity that we can extract from that, just because we are not even sure that the restricted connectivity is something that is consistent in a test we test. So next step in that would be to do task activity, looking at task activity with individual SATPAs. On the diffusion and magnetization transfer results, we have not found any significant changes with the spinal cord, not even within specific regions. We have seen a little bit of variation for every subject. You can see that there is a decrease in the inter-subject variability, but it was not significant. Motion did not improve, so we did not reduce motion, but it's basically because there is no, in these healthy subjects that did not move a lot, the motion that we see is related to breathing and swallowing, and the SATPAs does not help with that. The interesting effect that we have seen is that the SATPAs improve the gray matter and white matter contrast on the T2 star weighted images, and we are not quite sure why is that, but might be improvement on the T2 star blurring effect, but we are still investigating that. So in conclusion, we have shown with this short study that using side paths or any bath that can help with sensitivity artifacts can help in acquiring a better quality image for functional memory of the spinal cord, and it does not change the consistency of quantitative MRI matrix in the spinal cord. So thank you for your attention, and if you have any questions, I will be happy to answer.
Thomas? Actually, very cool, by the way. You also do the SNR analysis for the CPI and all the other.
And that was something surprising, but it actually reduced the SNR in these in the diffusion and the FTR. And
even what about the gradient you want to gradient?
Yeah. And I did not present that because there is not a proper, a really proper way of calculating the SNR in this matrix when we have side paths. Well, there is so many different ways of calculating the SNR that I didn't find something that was like I was happy enough with the methods to calculate SNR to present the results that I was confident. But with multiple methods that I use, it actually did not improve, did not decrease significantly, but was a trend to decrease the SNR. The matrix that we extracted for this.
Just a quick method question. So when you add the methods, I guess you have to read the answer, right?
Yeah.
Does that make a difference on what
definitely
metrics that you explain?
So we always so the positioning is different, and using side paths, you actually put something in the neck, and that's all the part of I was saying about positioning the patients. Actually, putting the side paths, put something in the neck. It's more comfortable for them. They're more constrained, so they move less. But also, the spinal cord is more straight when you positioning because there is bigger space in the neck. But yes, there is differences between without and without side paths when doing the position. So we have to reposition and readjust everything. Yeah. So that's also why the comparison is quite tricky because we're actually not comparing everything in the same way.
Do you expect loading the pads to keep the loading similar for local technique for
That's a good question. I don't know, and there was as well questions about if we can put the side paths in 70. If is it safe? So I don't know.
So I know these are very different materials that you're using for different purposes, there's different effects, but these to high dielectric materials to holds with.
These cost already $4,000, so we haven't tried anything else. But I know some people have tried rice pads and getting a better SNR for spinal cord imaging, but not as strong as that one. So I don't know if, well, that costs a lot, but is it worth it? For more, yes. For other things, maybe.
What is the electric properties of this? Is it just water or
it's a non-proteinated perfluorocarbon liquid, so it's basically the same material that they put in the lungs to decrease the. I don't know exactly what are the properties.
This was for the test, but I'm not percent.
Sorry?
This was for the test or?
It's right.
So just things in terms of the positioning for the comparison, maybe if you want to dive more into that, like using cushions or things that have like the same morphometry, would make the comparison in terms of like positioning.
Yeah, because one way of looking at the sensitivity artifacts that can be reduced is looking at the curvature of the spinal cord, but we don't have the same positioning. Exactly how they compare the motion to the artifacts. So,
Yeah, I guess another aspect is how the shielding is performed.
It all comes down to shielding, right? Yes.
Good. All right. Thank you very much, Benjamin.
The last our pitch will be given by Anna Combs or Anna Combes. Sorry, Anna Combes. From Vanderbilt Institute of Imaging Science, going to talk about functional connectivity at the 3T.
Alright, so I just started a postdoc in January at Vanderbilt working with Seth and John Gore. And I'm involved in projects looking at the application of resting states to clinical populations. So as many speakers today have already talked about, there's been considerable work in recent years in the development and optimization of functional methods into the court. Studies, including some by Rob Berry that he presented, have shown that we can reliably detect motor and to a lesser extent sensory networks in the cerebral cortex in the sequences, and that these are affected by the presence of pathology. So there was one study on multiple sclerosis patients. So once we have methods that are relatively robust and sensitive, the next step is to apply them to a wide range of diseases that affect the spinal cord. So our general aims with this in your lab are to first assess the retest reliability of our sequence at 3 Tesla, then to investigate this in, then to use these sequences to be able to detect differences between patient and control groups, and third, to see whether we can relate these measures to clinical symptoms. So at the moment, we just started a study in people with degenerative disc disease. This is an example of a patient. This person has compression of the cord at the C5 to C7 levels with no evidence of myelopathy, and this would cause symptoms like pain in the neck, shoulder, and arm area, and problems with sensation. So the study has just started, so I'm just going to present our basic design and then one example from the patient. So we will be recruiting and scanning patients 3 times over 1 year at 0, 6, and 12 months. We're doing structural imaging at 3 Tesla and functional sequence, and we are also doing full behavioral exam, including neurological testing, questionnaires assessing pain and functional impairment symptoms, pain detection, threshold testing, motor dexterity using the backboard, and we're also doing quantitative sensory testing, so to assess people's detection thresholds for detection with thermal stimuli. So here's some example data for the patient that I presented. We're doing anatomical imaging using graded nickel sequence with high frame resolution and good white gray matter contrast for segmentation. Then we're acquiring 2 resonance state brands using 3D multi-shot graded nickel. We're getting 250 dynamics, which takes around just over 10 minutes for 1 run. And this is an example of improvements in temporal signal-to-noise ratio that we obtained after basic preprocessing. So related that for 1 run after motion correction and after dental filtering to isolate the frequencies in the range of interest. I think for what is representing, this is a particularly good size and a good subject. All right. From our anatomical image, we get 4 regions of interest in the dorsal and ventral horns. And from these, we can extract time series corresponding to each region, and then we look at the correlation between each combination of these regions. So that's 6 pathways of interest. The most interesting to look at least at the moment, will be the number 1 and 2, which will correspond to the dorsal and most importantly the ventral one, so motor network, which is number 2. So here we have the distribution of our correlation values across all protein sizes for each of the 6 pathways of interest in a control and a patient. So this is just one subject with just started recruitment, so some of the next steps will be obviously getting a control group. We're interested in getting patients with and without myelopathy. And we'll also be looking at integrating the spinal cord toolbox in the pipeline because at the moment we're relying on semi-manual settings. I'd like to acknowledge my PIs, Cecil St-Longor, and my colleagues at Vanderbilt, and particularly Aaron and Danisha.
Maybe I'll ask the same question again about the slice thickness and particularly in this population, I guess, where you are at the level of the disc, gradient echo don't behave very well. And so I was just wondering whether you consider maybe going to thinner slices in order to mitigate this intravoxel inhomogeneity. I mean, at the cost of SNR, obviously, but maybe the in-plane resolution could be lower, I would say. So I just want to have your take on that.
I don't think we've tested that yet.
It's a common problem for all of us. Size thickness for gradient echo estimation, whether this is EPI or that's like standard results. Any other comments? Okay, good. So we can thank our speaker again. So the session of the power speech is over, and we are a bit late in terms of our schedule. So what I propose is that we take a little break now. I'm sure you enjoy some refreshment, coffee, and viennoiserie, and then we gather back at 11:15. Then we can just go straight on the spine generic study, and then conclude. And I would also like to thank again all our speakers for the power speech. Viennoiserie and coffee is right outside. Sorry for the remote people.
We've got our own tea here in Cardiff. It's all right.
they also get coffee, or? I don't know if they got coffee. Maybe I don't know. Okay, so let's get started with the second part of the workshop, which is about this spine generic protocol. So it's an old project that started I think in Singapore 2 to 3 years ago, and the goal was to establish a consensus set of quantitative MRI or semi-quantitative MRI acquisition parameters for the spinal cord at 3T. It's a bit similar to the NINDS CDE initiative that is focusing on the spinal cord injury, but the goal of that particular initiative that we're trying to work on here was not specific to a particular disease. So we're trying to really be as generic as possible, that's the term generic. And so of course, by having a one-fits-all type of protocol, you might feel that it does not cover your particular application. But again, the philosophy here is to really provide the community with something to start with, as opposed to just starting from scratch, doing 10 pilot scans on people and finding out what those artifacts, trying to look at to read the numerous papers of how to optimize spinal cord imaging and spend waste time, waste money, and so on. So really, it was to give people some starting points. And another important aspect is that we wanted this to be available for the 3 main vendors, GE, Philips, and Siemens, using the product sequences. Some might require particular license, but in general, most recent software and models are covered or can handle that protocol. So the protocol is accessible at this page, spinalcord.mri.org/protocols, and it's hosted on OSF, Open Science Framework. That has interesting features such as versioning system. So every time we upload the modified version of the protocol because we find bugs or inconsistencies, there is a file called changes that explain all the changes that have occurred. There is also a PDF file here that you see. It's called SOP for Standard Operating Procedure, and it explains how the acquisition setup should ideally be conducted in terms of patient preparation, patient positioning, where to do the endocenter, how many cushions, where to do the cushions. It also explains on sequence by sequence basis how to position the chip volume, how to position the FOV, and it's supposed to be, fairly well explained. If it's not, if there are things that aren't clear, please feel free to give feedback, because ultimately this document is mostly used by MR techs who are taking the pictures. And yeah, the other aspect that we'll cover today is that coming with this generic protocol are a series of databases. So two main databases. The first one is a single subject database that has been acquired with that protocol across different sites. And the other one is a multi-subject. So subjects acquired at different. Subjects were different across sites. And I'm going to present those results today. Briefly, what does the protocol consist of? It has a large coverage of brain and spine, 3D, T1 weighted MP range type sequence, which is a 1 millimeter isotropic sequence for that many people are familiar with and use it for their analysis. Another one which is a bit more focused on the spine region, and it also has a better spatial resolution. So we recommend that for chordatrophy measurements. A multi-echo gradient echo sequence to be able to basically improve, to increase contrast between the gray matter and the white matter. That could be used for doing gray matter cross-sectional area measures. A protocol based on magnetization transfer that is sensitive to myelin content, and so it could be used for demyelination, for following demyelination. So I want to mention this is a magnetization transfer saturation protocol. So it has an empty on and empty off, and it also has a T1 weighted image acquired with the exact same parameters, except the TR and flip angle are different. So it's 3 volumes instead of 2. And also a diffusion MRI sequence. I call it different tensor imaging because the one that is proposed in the protocol is a single shell, for the sake of compromising with acquisition time. But obviously, it's very easy to change the number of directions, add some shells if in your specific studies you would like to use more advanced models such as 3D or NoD. Total acquisition time. As I mentioned, we wanted to get something that is reasonable with the clinical constraints. It's between 20 and 30 minutes, and this time depends on the preparation, obviously, but also on the vendors. Some sequences run faster than others. So this is a result that I've already shown last year at the workshop in Paris. It was presented as an ISMRM abstract also by Stéphanie Allais. So this was me. So I was basically scanned 18 sites, and what I'm going to show you is the results of some of the quantitative metrics that we obtained So the first one is from the 3D T1 weighted MPRH, where a cross-sectional area was measured from the spinal cord segmentation and averaged between C2 and C3 vertebral levels. So at CCL you have the different sites. You see there is a lot of Japanese flags because I spent some time in Tokyo and happily benefited from all the scanners there. But there are also other sites in the UK, the US, and Canada. So one of the conclusions from this study was that the reproducibility across sites within vendors is quite remarkable. If we look at the standard deviation, which is here, so the first number is the mean, is the average across sites within vendors, and the second number is the standard deviation. So you see that we have a standard deviation of less than 1 millimeter square, which basically represents the size of the pixel. Right? So the precision is really remarkable. There are some outliers which are just due to the sequences not being used properly. Where in some sites we have activated some filters, and with filters comes a bit of smoothing, and with smoothing, obviously the estimation of the border of the spinal cord changes. So that explains part of the outliers. So those were acquired still during the optimization test, so it's kind of final. Second measure that we took was from the multi-echo GRE sequence to then compute the gray matter segmentation, and then average it across C3, C4. Again, the reproducibility is quite good. We see that the bars are jumping up and down, but you have to realize that the scaling is also very like the dynamic scale is very narrow, so we are ranging between 10 and 19 millimeter square. And as you can see, the standard deviation is also below 1 millimeter square for the within vendor variability. And another one is the magnetization transfer ratio, which was computed from the MTSAT protocol. In that case, this metric was averaged between the C2 and C5 vertebral level, and only within the white matter. So as you can see, there is some variability. So there is some variability on the GE side, because some of the sites did not enable to go with a shorter TR that was specified in the generic protocol. So in some sites we have to change the TR, and when computing the MTR, we know that because of the contribution of the T1 effect, we also get a different MTR. So some of the variability comes from this change in TR. The inter-vendor difference could also partly come from the fact that the empty pulse is different between the GE and the Philips Siemens sites, which the first one is the Fermi pulse, the two others sync pulse, if I'm not mistaken. There could also be slight difference between the Philips and the Siemens in terms of the timing of the pulse and its shape. But overall, the coefficient of variation were less than 10%. And it was actually 8% for GE, 8% for Philips, and 3% for Siemens. And last results of the single subject was for the diffusion MRI scans. Again, the metric was averaged in the white matter between C2 and C5 vertebral levels. And that was, and here we are looking at fractional anisotropy from the diffusion tensor. Results are more reproducible than for NTR. There are again some outliers that are due to the way the protocol was set up, the accessibility of some of the software version that that did or did not allow a particular feature in the sequence. For example, the use of the saturation bands that was not properly put, or sometimes the pulse oximeter was not used, and that partly contributed to some of the variability. But in general, the coefficient of variation, if we exclude the outlier, was respectively 1.5 for GE, 4.2% for Philips, and 2.8% for Siemens. So then let's dive into the main purpose of today's workshop, which is this multi-site, multi-subjects. As you can see, there's a lot of logos, and some logos are added as we also advance in time, because there's more and more sites participating in it. The goal of this particular multi-site, multi-subject study was to evaluate the efficiency of the protocol. So what I showed you right before was basically I went to different sites. I told the MR tech, how to position the FOV. So this was more an assessment of efficacy. So basically, the best conditions possible, what kind of variability do we get? And also, it was the same subject. So we did not introduce any variability in terms of intersubject variability. So this was really the best of what we could get. We wanted to be a bit closer to a more realistic scenario where people would just scan 40 MS patients, which are different patients, which are scanned in the sites that does not necessarily have the expertise to scan spinal cords. So that study was really to try to get a closer overview of the coefficient of variation that we get if we're to use that generic protocol in any site of the world. Corollary advantage of that or goal of that project was to provide a publicly available database, which could obviously be used for generating normative values. So having quantitative values to compare to if you were to scan patients within the same demographic distribution. But it could also be used for developing new analysis methods for segmentation or others. Dataset. So the specifications that most of you in the room are already aware of, because many of you have contributed to this database, was that it would be composed of 6 subjects per site, 3 males and 3 females. There is a slightly bit of variability. Some sites contributed to a bit more data, but we are very inclusive. And the other aspect was the age range, because we know there are some morphometric and possibly microstructural differences across age. So we wanted to try to narrow a little bit this demographic. It's also easier to get grad students to get scanned. So currently, the number of sites that are included in the already existing database is 32. 4 sites have confirmed that they would also contribute to this database, and 5 might also contribute. So at the end, we might get something like 250 subjects. So again, this is not too late to participate. If you feel you would like to contribute to this seminal database, send me an email, and it's pretty straightforward to get things going. There's obviously an ethical consideration here because it's a public database. So there's of course anonymization of all the data and the defacing of the 3D NP range that includes the edit. So as I mentioned, the data is already available. It's on OpenNeuro. I decided to not, so as some of you might have noticed, I first uploaded the data on OSF, on Open Science Framework. It had a couple of limitations. Don't want to go too much into details, but it basically does not allow for uploading large files. It's difficult to fetch individual subjects. So if we upload each subject individually, it just gets a bit messy. The versioning system is not as well established as OpenNeuro. So OpenNeuro is, I think, a great resource for specifically for MRI or like large imaging data. So we are happy to be hosted there. Each subject is about 25 to 40 megabytes, and the total size as of now is about 7 gigs. One thing that took us a lot of time was the structuring of the data. So obviously, a database that is a bit messy is not really useful ultimately. We wanted to be fully bit compatible. So for those who are not aware, this is an initiative that has been started a couple of years ago, led by Chris Gorgolewski at Stanford, and it suggests a way to physically structure the data, to put them in particular folders, name them in a particular way, which could be annoying for as a start, to have this kind of a barbarian names with ACQ and so on. But at the end of the day, this is a convention, right? And more and more people are adopting this convention for their imaging standard. And having the same convention makes it easier to share data. If you acquire data from another site, or if you want to share your data with others, and your processing pipeline is organized in such a way that it will read a file that is called sub-star something, and you know that it could have specific contrast inside it, specified folders, and then DWI, fMRI, and so on. You know that your analysis pipeline will work in a bits database, and that's a huge advantage. It's really a huge advantage. So we make sure to follow that convention. It was not easy because this initiative is constantly under evolution. So they received, there's a lot of active discussion about integrating more QMRI techniques into the bits format, because it started with a more fMRI population, I would say, like the typical OHBM profile. They like to do a lot of fMRI, but not necessarily a lot of B1 plus mapping or MTSAT and things like that. So these were not covered by bits, and as a result, they were not bits compatible. So nowadays there is like new initiatives, notably the bits, the BEP001 initiative that tries to bring more quantitative MRI data inside the bits convention. So we follow the lead of that, but we are still not fully compatible, notably with those NT-off, NT-S, and so on. So for that reason, we had to add a file that is hidden. It's called the bits ignore file that basically tries to be bits compatible by ignoring some of the files, the structures. Just giving you those details in case you want to dive a bit more into the bits. Okay. In terms of processing, the analysis pipeline is fully automated, and it is also open access and open source. So if you click there, you will have you'll go to the GitHub page that basically gathers all the scripts that were used to process the data. Just for like interesting technical detail is that all the subjects can be processed in about 6 hours using a parallel computing. And if you have any questions, suggestions on the processing pipeline, please send feedback on the GitHub issue webpage. So I'll give you an overview of the pipeline. So it starts off with the T1 weighted NP range, and the goal is to register it with the Plan50 template that has atlases and templates that can be used for computing the metrics. For example, the white and the gray matter atlas are used to basically compute the specific metrics inside tracks. So first of all, the segmentation is done using the recent deep learning based SCC DeepSeg SC function. Then there is a virtual labeling that is done on the T1 weighted scan, and from the segmentation, the virtual labeling, we can then estimate the warping field that brings the template to the subject and the subject to the template. So it's a bijective function. Then from this information, once we bring the template into the subject space, we can then ask to compute cross-sectional area between, let's say, C2 and C3. Then we bring the T2 weighted scan into play. We run the same function to compute the spinal cord segmentation. We register these scans with the template by using the initial registration from the T1 and Plan50 scan. And once the T2 is registered with the template, we can then estimate cross-sectional area within the same level, so C2 and C3 as well. Next scan is the multi-echo GRE sequence. So we average all the echoes if it's not already done by the vendor. Then we compute the gray matter cross-sectional, the gray matter contour to compute the gray matter cross-sectional area, again by bringing the template into the multi-echo GRE space by using the pre-registration from the T1. Next scan is the NT-SAT protocol that has the NT-off, NT-on, and T1 weighted. First of all, we co-register them all together. Then we compute the segmentation from the T1 weighted scan. Then we can bring the template objects into this space, and then using the white matter mask to compute the different MT-based metrics inside the mask. And we do the similar way for the diffusion weighted scan, where we start with the inversion correction, segmentation of the mean DWI scan, and then registration between the Plan50 template in order to compute the DTI-based metrics inside the white matter. So first question that comes, of course, obviously, is, well, that's, sounds good in paper, but, when I try it, does that work in 100% of the case? The answer, obviously, is no. So we need a solid QC quality control framework for that. And so we are using the SCT's QC framework. It basically shows in a web browser all the processed subjects and the different output segmentations and labels and registration and warping of the templates into each subject. So I can show you a little bit in live example how that was done. So basically, when you run the pipeline, you have as outputs so these are the data with all the well, they are not all of them because they're on the cluster. So, but normally you have all the list of data here, all the list of subjects, and you also have a QC folder that includes an index HTML file that you can open with your browser. And okay, and then you have the list of subjects here, and you can basically use your like the arrow to go up and down and check the different processes. So, for example, the core segmentation, the warping to the template. You can also use a filter to just look at the vertebral level, for example. So here I'm only showing the vertebral labeling across subjects just to make sure that they all run properly. And if we spot a problem, then we would basically identify the subject and manually correct for it. And once we correct for all the subjects, this manual correction, as you can see here, there is, for example, a problem, right? So the procedure would be to ask for manual labeling. We do the manual labeling, we save it in a folder, and then we rerun the entire processing pipeline, and the processing pipeline will use the manual labeling if it exists, right? So that enables to ship as a package the original data, the processing pipeline, and the manual corrections as a whole package that enables to reproduce entirely the results that you're seeing here.
Yeah. For this subject, do we know why there's a problem? There was a question about that a couple days ago on the forum. So, like, what's going on with the algorithm here?
Yeah, that's for sure. I'll need to go back to it. It could be something with the straightening. It could be something with the scaling. Maybe normally
Isn't the subject too small, for example?
So yeah, because the way it works is that there is first an initial identification of C2, C3Ds, and then there is a template-based, identification of the subsequent superior and inferior disks. If there are, and this location is based on a probabilistic location from an adult template. So in some cases, if they are, like a bit outside of the probabilistic, distribution, maybe they are not properly found. Which that's again, I will need to get into that. Sometimes there are bugs too. So yeah, in case there are bugs, we need to fix them.
This subject is not the base.
You see the sorry?
This subject is not the base. You mentioned
right. So that was the discretion of the sites. It's a good point. So some sites did not deface. Yeah. Okay. So let's go back to the processing. So an interesting statistics is how many numbers for how many numbers do we have to go back and do manual corrections, and that also gives some insights about the quality of the imaging and the robustness of the protocol. So for the T1 weighted MPRH scan, we had to go back to manually correct 17 cord segmentations, which represents 8% of the cases. And as you can see, for the T2 weighted turbospinico, like the space type sequence, it's only 2 subjects. So the robustness was quite remarkable. And I'm sure many of you are not surprised by this result. When you look at an MPRH, you see that it's very sensitive to cord motion, to swallowing. So it's not surprising that automated segmentation would fail there. The gray matter segmentation was, I would say, reasonable. We had to go back in 15 subjects, which corresponds to 7% of the population. The T1 weighted axial scan, that is part of the anti-SAT protocol, we had to review 4% of the segmentation. So that was, in general, also very robust in terms of segmentation. And the vertebral labeling that we just discussed was we had to review to basically correct that in 25 subjects. I should also mention that we probably need a QC on the QC. So this was done in a rush to make sure the screen all will be ready before ISMRM. As you can imagine, you know, there are some flaws in working like in a rush. So we want to basically redo all the QC and spend more time on the results. There is also standard operating procedure for how the manual correction in QC was done and how to operate. So, interesting. So the question you might ask was, you know, what were the kind of problems when we are dealing with multi-site studies? They could be various. So one problem was that sometimes people would label MT off as MT on and the other way around. So obviously that's a problem when we compute the MTR because it becomes negative. But that's a very easy outlier to discover. That you have all the statistical results and you have a negative MTR somewhere, so you know that you have to go back to the data and to manually change it. But that's part of the manual curation. Bit more tricky was that I've seen that in 2 to 3 sites. Some subjects is that there's a misplacement of the field of view between the MT on and the MT off. And that is a problem because the processing pipeline that I showed you assumes that the subject does not move too much in terms of in inferior superior direction. It might move the head a little bit, but that's accounted for by the fine-tuning registration. But if the FOV is not centered in the same way, then the registration between the MT on, MT off, and the brain activity T1 weighted will basically not be exact, and that that could cause a lot of problems in the output metrics. So you could think of automated way to check for this. For example, like running mutual information metrics on the entire volume should probably tell that there was a big misplacement in those cases. So there is some room for developing better automated QC algorithms. If some of you are excited by developing those, we need help. Yeah. What I saw also is that 2 subjects were mixed within the same subject folder. So obviously that created some issues in the output metrics in the end registration. A bit more tricky to debug is that in some cases, what I noticed is that the shading settings were not the same between the MT off, like within the MT set protocol, and they need to be the same for multiple reasons. Because the basically that it is possible that the overall scaling of the image might have changed. The coil sensitivity profile is adjusted for a particular field of view. The fact also that not all the same coils were used between the T1 weighted and the MTR protocol might have caused different noise behavior or also image intensity scaling. And that's a problem because at the end of the day, what we do is we compute ratios between MTR and MTR and T1 weighted to get those MTR metrics. So that could contribute to the variability of the observed results. And again, thanks to the BITS organization, to the BITS convention, this is easy to check for. We can just include in the BITS validator verification that within the MTS protocol, all the sheet settings and coils are the same. So it's a couple of lines of code, but if someone is interested in contributing to this project from the processing side, we would really welcome those contributions. And then we observed some weird stuff happening. Not exactly sure what I think happened in those cases is that maybe there was a different placement in the Z direction between the diffusion scans and the T1. So basically the physical coordinate system and the voxel coordinate system was not matched. That was some problem. But yes, these obviously these subjects were removed. It only happened in a few subjects. Then there are things that I'm still not sure what happened here. Very strange. So what you're seeing here is the coronal view. Like the FOV is supposed to go from there to there. And that's the sagittal view, and as you can see, the core is just. I don't know what's happening here. Yeah, so those needs to be investigated. In some cases, there was poor shimming, and that's a scan acquired in Montreal and on the G system. And as you can see, if the shim box is not, positioned in a proper way, then you just end up with, almost pure noise. And what I'm showing you here is the B0 of the diffusion weighted scan. The diffusion weighted scan is basically like salt and pepper, so there's almost no relevant information. And common problem also is obviously image quality, motion. That happens. So I'm just showing you some GRE scans. But this happens also in the T1 weighted MPRH, swallowing motion. Like natural cord pulsatility as well, which in some subjects is a bit more prominent. And yeah.
When I was acquiring data in Minneapolis, I have observed this issue happening mainly on small tiny persons. I had issue with women, which were small and low weight. Those artifacts were with high power.
Okay. Interesting. Yeah. But subject preparation in those scans is key because this is a fairly long sequence. It's almost 5 minutes, and if people move or swallow that sequence, if the shimming is not correct, it can lead to images. So, I'm going to show finally some results. Again, you can reproduce all those results by yourself by downloading the data. So what I'm showing you is version 1.0.0, and as we go through the data and add more sites, this number is going to change. But you can reproduce those results if you're using that version of the data set and that version of the processing pipeline. And if you go on the GitHub website, you'll see that the release, this release has a binary file that has the manual correction. So you will also be able to download the manual correction of the segmentation and datable labeling to rerun all that. So, showing you a mosaic of image to get a snapshot of all the subjects from all the sites. So these were flattened in the basically the right-left direction, so that we can see the cord in all the scans. And there is also like a histogram equalizer algorithms, like a patch-based histogram equalizer that was applied in order to be able to compare all the images and to focus really on the level of artifacts and motion and things like that. So what you can see, first of all, is that not all the subjects were positioned in the same way. If we now go to the quantitative results, so it was the same as for the single subject study. So the cross-sectional area was averaged between C2 and C3. And so that's the result. Finally, for the Q1 weighted called cross-sectional area, the black is GE, blue is Philips, and green is Siemens. You can see the over-representation of the green. So we are really asking, GE and Philips side to contribute to have a better representation. If you have Canon, Toshiba, or Hitachi, please contribute as well. We would like to have other vendors. The model of the scanner is indicated here. So MR750, for example, Signal, Achieva, Ingenia, Prisma, PrismaFit, Trio, Vario. And so a couple of comments. I'm not going to go through all the details, but so what you have on the top of the mean here and the standard deviation there, okay, for each vendor. And what you see here is the coefficient of variation. So there are two COVs. The first COV, the first coefficient of variation, is the intra-subject. So for each subject, intra-site. So for each site, we computed the coefficient of variation, right? Because each red spot is one subject. Okay. So we had enough subject to compute the standard deviation, which we divided by the mean, to have an intra-site coefficient of variation. Okay. And then we also computed the inter-site, but within vendor coefficient of variation, by dividing the standard deviation of the average per site by the mean of the average per site. Okay. And not surprisingly, the inter-site coefficient of variation is usually smaller than the intra-site coefficient of variation because of the the inherent subject variability. We know that curved cross-sectional area does vary quite a lot across subjects, right? So that's not surprising. But interestingly, we get, and this is really an assessment of effectivity. So each site downloaded the protocol, scanned them. They usually emailed me not very much. So it was really realistic implementation of a protocol in situ. And you can see that the standard deviation is less than 1.6, 1.5, and 2.5 for Siemens. So and this is in millimeter square, so fairly good precision. And the question of variation inter-sites of 2.5, 2.1, and 3.7 respectively for GE Philips. So that's pretty good. Let's move on now to the T2 weighted scan. What you see here is an axial view of the T2 weighted. So it's a turbospinico scan. That is accelerated. Takes about 4 to 5 minutes to acquire. It's a 0.8 millimeter isotropic resolution. Yeah.
The slide for you or anyone with you is when you're for like defects for pathologies.
Excellent point. The answer is so So the short answer is no, but we did notice some effects, and we know that the asymptomatic degenerative peripheral myelopathy is quite common. So we did have people with that. So that needs to be done indeed. That needs to be done. Yeah. Yeah.
So it's not part of the supervision protocol. So your abnormalities.
No. No, it was based on the trust from each side. So each side, basically, committed to share data from, so supposedly healthy individuals and so on. Yeah. So there is more details in terms of the manuscript about the inclusion and exclusion criteria, like the typical one in terms of neurological disease and so on. One thing to mention is that, so as I said, we are using a patch-based histogram equalization algorithm with a fairly small window of 16 pixels. So it's possible that in some cases we would see a spurious increase of signal in particular region. So we just need to be careful with that. Yes?
I was going to say, I think the approach that I would take for that is that the subjects that I'm scanning for my IRB, it says in the IRB that the people scanning are responsible to, pointing out any possible, pathological concerns and bring it to the radiologist. So I did that before I ever gave my data to do it. So I'm taking responsibility for that.
Sure, but there's also 9 changes that you put into here. I'm not sure that's really what we're trying to measure. Or maybe you are.
Right, that's a thing to verify. So yeah, we're definitely going to add this in our to-do, which is already 3.5 kilometers long. So results. Same measures, cross-sectional area between C2 and C3 from the chord segmentation. These are the results. Oops, I'm sorry. Spoiler. First of all, we can see that the 3 vendors are a bit more consistent. I did not compute the inter-vendor variation. That's something we could add. The coefficient of variation was 7.8, 7, and 8.6 for the intra, and the inter was 3.2, 2.2, and 4.5 for GE, Philips, and Siemens. One question that comes regularly when in studies looking at cross-sectional area, and which is an extremely used marker for MS, for example, is what happens if we compute cross-sectional area in the T1 versus the T2 HT scan? They seem different. How much are they different? And what if I use GIM instead of SCT, instead of another software? This is an important question, and so we dig a little more into that, and we looked at the level of agreement in a cross-sectional area between the T1 and the T2 HT scans. Having this population now enables to basically explore those interesting questions. First of all, we can see that there is definitely not an agreement. So I'm showing the Siemens here. I'm going to overlap the Philips scan. So as you can see, there is a fairly good overlap between the 2 vendors, and the GE is a bit less of an agreement. To be fair with the GE center, we should also mention that they are having different sequence parameters in the GE for the GE scanner that were used, and that contributed to the variability that we're seeing here. Right? So by making sure we remove those variability across models, across the GE models, we will also minimize that. But that's the first observation. Now, if we try to to fit this agreement for each vendor, we would basically get an R square. So for the vendors where we are a bit more confident in terms of the parameters that are followed across models within vendor, we have an R square of almost 0.9, which is fairly good. And some of the outliers are, again, due to possibly some glitches in the segmentation that were missed during the QC. So these are things to consider. But you know, we could definitely benefit from such plots in a sense that if people were to start, let's say, like a multi-center study where, like a retrospective study where they have access to T1 weighted and T2 weighted in different sites, maybe there is a way to actually use all the data, even if the protocol is not exactly the same. So that could be of interest. Yes? Yeah, that's an excellent question. I can tell you by looking at the numbers at the trends, I think. So for the T1 was about 60 to 70. Whereas in that case, it was a bit higher. So the T2 has a higher cross-sectional area, which means that the T2 would be then this one, and the T1 would be that one.
We know which one is correct.
Yeah. Is it an average? Is one slightly overestimating and one slightly underestimating? Or
Right.
one really and the other one five?
Right. So that's yeah. There's again a continuous debate in many spinal cord segmentation papers in the discussion section. This is mentioned. One thing, you know, like just as an example, the T2 weighted scan, for example, is T2 weighted, but it's something that was raised with, in discussions with the people at UCL, where they actually raised the point that the PL matter has a very short T2. Therefore, if we use T2 weighted scans, the PL matter would appear as very dark, and that would change the gradients at the interface between the core and the outer part. So all these little, and as you can imagine, if we slightly change the TE, that would affect, you know, where we set the boundary for the core. What is the ground truth? Yeah, I don't know. I mean, I guess ex vivo, like super high res, 70 images could maybe address that.
Well, at the end, it doesn't matter. We don't have to make it
That's good. Can you try to note T1, T2 on the... Good. All right. Let's move now to the diffusion MRI scans. So don't pay attention to this. This is just a glitch in the mosaic creation software that didn't take into account the pixel resolution properly. Also, what you see is that sometimes the contrast is a bit different. That's again because of the clay histogram equalizer. But overall, what you're seeing here is the mean DWI, okay, after motion correction. So, yeah, I'm pretty satisfied with what I see in terms of those ugly fat, like neck fat, that sometimes will be overlaid on the spinal cord and things like that. I find this to be fairly clean, I would say, across sites and across numbers. If we look at the fractional anisotropy, that's I think also fairly encouraging with an inter-site within vendor coefficient of variation of 4.5 for GE, 1.9 for Philips, and 3.7 for Siemens. There are again some glitches that we need to go back and address. For example, some outliers that might be due to issues in the segmentation or motion correction. So there is a lot of QC freedom. In fact, the number of images that we had to review was about 1,500 volumes, not counting all the different labels and so on. So that's quite a massive amount of work. What I did not mention is the number of subjects that are removed from what you're seeing here. For the T1 scan, I removed only 2 subjects. For the T2 scan, I removed 1 subject. And for these results here, I removed 3 subjects. Okay. So it's not a lot. So results now on the magnetization transfer in terms of data quality. So what you're seeing here is a mosaic of the MT on, T1 weighted, and MT off. The fact that they are not aligned is just the way the mosaic generation software works. But after we programmed this little visual interface, we realized that it would be a nice way to assess the registration for the MT-SAT protocol. So that's something that we should work on. But yeah, so in general, we do see much more variability across vendors in terms of the generated contrast for the MT on, for the MT off, and that's obviously translates into more differences in the MTR calculation. So that's what we see when we do the quantification of the MTR. First of all, there are again some outliers, which are again due to the fact that the TR was not set. So in that case, for the Stanford case, the TR was 105 milliseconds. Whereas for the other GE sites, it was about 35 to 40 milliseconds. So that obviously creates a different MTR. So it's not necessarily wrong. It's just different from the other sites. And so in that particular case, I removed 2 subjects only, and I do see a bit of a difference here, which I'm still not sure where it comes from. I checked the parameters; they are the same. So I was just wondering whether there could be a difference, and that's I'm asking the Philips experts here if across version the MT pulse might actually change, or if there could be something else that could explain that.
The ratio is, I think, is dependent on the preparation, like entry preparation. Maybe if the scheme is different, like we could see different MTO results.
Yeah, no, so exactly that's what I was wondering about. But so this particular version was 5.4, which I believe was also used in other sites. So yeah, still it needs to be investigated. I'll probably put in the loop our Philips friends there. Yes. And from the MT-SAT protocol, so we calculated the MTR, which is basically the normalized ratio between the MTR and the MTR. If you want to compute the MT-SAT model proposed by Helms and al, that is supposed to account for the T1 variation, and supposedly gives less dependency on the V1 plus effect and T1 effect. We do have, in fact, more variability than with the MTR. So the correction, the variations are much higher than for the MTR. Yes.
The talking of the scanners in one group, or how it happened that there is also drug
those outliers. So for this, for the MT-SAT results that you see here, I removed the same 2 subjects as I did for the MTR. So it is, I should probably go back to look at those outliers here. But yeah.
No, I thought only the Tokyo group that there is.
The fourth one from the end.
This one? Oh, yeah.
There is lots of dots, and one half is around the main, and the second half is about the main also.
Are you talking about this mean?
I mean, there is more than 6 dots, so.
Yeah, so some sites contributed to more subjects.
Yeah, and is it the lower part is one scanner and the higher part is second scanner?
We need to check. Can you note that, Alex?
Yeah.
That's something we need to check. But as far as I remember, I think the Tokyo site only contributed to six subjects. So I'm not sure what's going on here.
But you have 2 institutions.
Right. So they were probably gathered. So that's probably a glitch in the.
So you're mixing 2 institutions.
Yeah, exactly. So that's. Thanks for pointing out. So I missed that actually. Yeah. So can you move like this down? Yeah. So that's a mistake. Yeah.
On the first platform, when you compare scale between 2 different sequences, you need to be careful with scaling. So maybe that's something that we double check. You have to make sure to apply some scaling factors to comparison.
Right, because
it's not a problem for the MTR because it's the same sequence on up, but that play a role.
Yeah. Okay. Cool. So that's something we can check. Can you add it, Alessandro? So checking the scaling between the MT on, MT off, and the T1 weighted for the Philips scans. Good. Last one is the T1 mapping coming from the anti-SAT protocol, which is also, not very encouraging. But again, we need to go back to the data and see what could be the problem. But my gut feeling is that the MTR was definitely the most precise. So there are still things that need to be done in this study. First of all, the single subject data. Ideally, we would like to reprocess it using the updated pipeline, and also we need to upload the data on OpenNeuro. So that's still needs to be done. For the multi-subject data, as I mentioned, we need to further interpret results and site-specific differences. So the sites will be put online. So look at them, give feedback, and let's get the conversation started. There's manual corrections. We're definitely aware that some of them are still not perfect, and crowdsourcing. So if there's some generous souls, that want to spend time there, would be really appreciated. And again, if other sites want to contribute to this, now is the right time. So please come forward. And yeah, as I mentioned too, that we should, and it would be easy to add some automated validation steps for making sure that the protocol was followed as in the specifications. So general to do is to finalize the manuscript. As many of you know, there's a manuscript that has been started, I think a year and a half ago, almost. And I think we're getting to the end now with those results. Obviously, before submitting it, we just want to make sure that things are properly fixed. And yeah, that's just a matter of people to discuss. Discussions that we could raise from this study is in terms of cross-sectional area. Well, so Rob actually asked the question, which one is more precise, or which one is more accurate? Well, one thing we could get from the study is that T2 weighted is definitely more precise than this one. I think it's the fact that this sequence is less sensitive to motion, and also it has better resolution, better spatial resolution. So I would tend to encourage using that over the T1 weighted MPRH for computing cross-sectional area. Some groups like to use the multi-echo GRE scan or axial scans for computing cross-sectional area. An obvious argument is that there's better intent resolution, usually 0.5 compared to 0.8 or 1. But there is also the disadvantage of having thicker slides, so we are more prone to a partial brain effect if some points are already curved and so on. So just a bit of food for thought. Regarding the diffusion weighted scans, just a bit of a technical point that I run into when doing the processing. At first, I was using the restore algorithm that was provided by Derek Jones that estimates the noise and then find outliers in the fitting algorithm in order to remove some of the outliers and obtain a more robust FA and MD and RD and so on. What I found is that in very few sites, the algorithm would actually fail by estimating the noise. Could be due to the fact that depending on what coil was used and combined with the acceleration, the noise estimation didn't work properly. So that does raise a question about how do we estimate noise for those kind of algorithms in these kind of studies where people are using different acceleration algorithms and also coils. So to solve that problem, I did not use restore, and I just used a simple implementation of the diffusion transfer. But feedback is welcome. For the grammar cross-sectional area, what I noticed is that there are reproducibility on the field scans. But I also, looking at the images, the contrast was also a bit lower. So maybe that's something we could discuss. Yes, Benjamin?
I'm wondering if there is a way to disentangle the variation that you get from the scan variation you get and the errors that you get using like a pipelines. I'm thinking about the grammar CSV because there is a lot of errors that you can make when you compute the grammar of this notation. There's the accuracy of algorithms. Is there a way to separate both of them?
I'm sorry, so to separate the
variability that you get in your results that depends on the scanner, that depends on the pipelines, the methods you use to calculate it.
Well, I guess the manual. I mean, yeah, that's yeah. I mean, it's possible. You could imagine like several raters. That manually scans, and then if there's a higher inter-rater difference, maybe that means that the scan is less reliable. But I don't think I have the energy to to dive into that. But it's definitely an important factor. Yes.
Sorry, maybe did you show something about it?
I did show something, but I think Benjamin's comment was about the.
No, I'm saying I didn't catch the area or I didn't see any results on the grammar.
Oh, did I forgot to? I'm sorry, I did forgot to put the slides in the grammar.
I was first about any.
Well, I can show you the plots. Here you go. Here are the results. So now it makes more sense what I was saying about the field scans. So I did notice a bit less contrast between the white and the gray matter. So I'm sure by working a bit more, we could improve that. But in general, for the J and Siemens, the inter site was reasonable.
And
I have to. I can tell you. I can tell you how many subjects I removed. it's for GM. I did not remove any subjects. I did not remove any subject for the gray matter. For the gray matter. Yes, Benjamin?
If I can go to my idea of trying to see what is the error that we made on the cross-sectional area of the gray matter. If someone wants to try something that we can mix both MRI workshops results, we had this challenge of gray matter segmentation. We can try different methods. For that, see the difference between the methods for all the 200 subjects. See the variable is. So if someone wants to do that.
So keep that as an idea for the next year workshop topics, and then we're going to discuss. And finally, the for the so-called Myelin mapping techniques. One thing that is important to keep in mind is that even though MTR seems to have a lower intra and inter-subject coefficient of variation, it's worth keeping in mind that it might also be less sensitive to demyelination changes. So if the contrast is flat and not sensitive to pathology, it's not really useful. So, and in fact, Jennifer Campbell shows on her paper on the pitfalls of G ratio that the anti-SAT seems to be much more like a better surrogate of myelination than MTR. And we know that now there's the multi-equal rays or other sequences that could potentially be replacing or supplementing MTR. So there are some perspectives to consider. The multi-subject data, as mentioned, this database could be used for normative values potentially. So I hope that researchers will start maybe benefiting from this open database. And as was mentioned several times, it also opens the door to further investigate how to normalize CSA, how to compare it across contrast, and so on and so forth. And yeah, the goal is also to use this open access database for creating challenge, like was done by Ferran Prados, the Gray Matter Challenge. But we'll probably have about 250 subjects with 6 different contrasts, actually 7 different contrasts. And our plan is to also upload the ground truth so that we all work with the same ground truth. So I'd like to have your thoughts or suggestions on that. So that brings me to the general discussion. What I'm planning to talk about is the Gray Matter Acquisition Challenge, which needs to be discussed. Some few updates on communication platforms. What's next for the next workshop? And if you would like to add any item on the agenda, feel free to do so. You can think about it and just tell us that you would like to discuss something before the end of the session. So first point is the Gray Matter Challenge that was presented at last year's workshop. I had some homework to basically finalize the processing and manuscript and so on, and I know that I've been dragging this because of other duties, so I apologize for that. But hopefully this will take after this rush, and by the end of this summer we'll be able to finalize this project and submit the paper. Updates on the communication platforms. As probably most of you know, there is now a website, MRI.org website, that has a couple of fun things. 2 days ago, where there is, we added this Slack channel. The Slack channel actually already existed, but like 2 years ago there was some sort of activity, and then it just died out. And then Benjamin was like, well, actually, there's a lot of Slack aficionados, so let's revive it. And I think it's a great idea to revive it because Slack has some benefits for very rapid communication. So click there and then participate to the Slack communications.
Maybe like the idea we had is really to have a common place, not just like the forum, but a common place to pitch ideas. If you have a new paper that you want to advertise, or if you have seen a new paper that you want to discuss about, Slack is a great place to talk about that. If you have issues with the pharmacogenetic protocol, it's a great idea to put an issue on a website. It's also good to have direct access to people on Slack. It could be a really good platform to increase communication for MRI. So I encourage you to go on the websites, register, create a few channels, we'll create some that we think could be relevant, but you can as well create channels.
Yeah, it also feels a bit less informal. Like if you have a question, but you don't want to openly open like a topic on the forums. It sounds very scary. You can just ask short question on Slack. So in addition to Slack, there is a forum which you can access from here, and we've added some nice logos and a new feature that has some announcements, topics, all the questions about MRI acquisition. So apparently, nobody has any issue with MRI acquisition. Topics in there. But please get this started. It's really a good platform, very useful platform to keep the discussion, having an organized tracking history of all the discussions. So everything at the same place. And there's also a list of all the workshops. And I will upload my slides in this workshop page, so you'll have access to those slides. Finally, what's next? So talking about next year, I was looking at the number of hours to go to Sydney, and then I realized that there was no direct flight from Montreal, and it's about 23 hours from there. So I'm not entirely sure that they will make it to Sydney. And in parallel, Ferran Prados at UCL is also willing to organize a workshop in London, UK. And I think the dates are pretty much fixed now. So you can probably safely mark your agenda. And it is likely that there won't be any workshop after ISMRAM next year. So I would say the May 2020 workshop will be in London. And main organizer will be Ferran Prados. He suggested a concept where people would submit some abstracts, and then you would pick some of them for our pitch presentation. It's going to be a 2-day workshop, so we'll have more time for discussing about the spine. Ideas for topics. It's open. Please feel free to give your feedback. We're thinking of killer applications for 7T, talking about atrophy of the gray matter, whole cords, how to normalize it, and so on. Talking about vascular diseases, talking about lower cord applications, thoracic and lumbar. Maybe we could focus on that. Maybe topics on histopathology as well. So you're welcome to chip in, on Slack or on the forum if you have some ideas, suggestions. Also, it was raised by one of the attendees that maybe it would be a good idea to give a certificate diploma for all the attendees of the workshop. In some cases, it could also be useful for as it brings credits for particular programs. So let me know if you feel this is a good idea. You can basically put it on the forum or on Slack if you add your +1 of this idea. Then if there's a critical mass, then we'll definitely make the effort to do it. Maybe additional comments on the yes?
If you suggest doing a substitution, I just want to ask, does the workshop give a CME?
So, like, I would have to verify what would be the specifications to follow in order to be able to give that. I don't have the answer now, but if you're willing to maybe investigate what would be the criteria to respect, it would be appreciated. Yeah, Nico?
Just a quick question that I was looking for earlier. When you were doing your own stuff, did you ever start rolling into the game stuff?
I didn't present the results there, but it was not great. I mean, it was fairly similar to what we saw on the multi-subject, multi-site. Same
thing. I didn't really get why you were saying that the vision that you do is better than the one in terms of precision of measurement. I mean, because of intersubject. But why you were saying that the vision two is better for than the one.
Okay. So yeah. So the thing is, there was not only a higher inter-subject variability for the MT-SAT.
No, sorry, I'm talking about T21. And you said that you think that two acquisitions for total area are better than one in terms of precision.
Okay.
And I didn't.
Right.
That's why.
Yeah. So my gut feeling on that is like I would say twofold. The first one is that the T2 is I find it much less sensitive to motion, like swallowing, hand motion and pulsatility of the core. And the second one is that it's also a higher like spatial resolution. It's 0.8 millimeter isotropic as opposed to 1.
So not from the numbers you got. It's not from the numbers you got.
I see what you mean. Actually, so yeah, I see what you mean. You're right. For the, I would have to go back. So we are a bit late now, but I'll have to go back. But I don't know if I mixed the two, but I don't know if it's the intra or the inter COV, but one was better. So I think it was the. Yeah, I think it was the intra-glandular inter-site COV that was better for the T2. But you're right that they looked fairly similar.
No, because the general point about this is that I don't know how much you can improve in terms of, I mean, inter-subject variability can be real. So you actually have a data that are very variable because your subjects that are. So maybe you see differences in the subject that are real. So,
sure, but the thing is,
it's good to have.
Sure, but it's also, I find it quite like looking at the inter-site, by like averaging 6, 7, 8 subjects within the site.
Yeah, but what I'm saying is that they are different subjects. So.
They are different subjects, indeed. For the single, when I scanned myself, I did find that there was better precision for the T2. Yeah. Okay, so if there is no other comments, I would like to acknowledge the workshop organizers, and especially I would like to give a big round of applause to Alexandre Foyas, who was extremely helpful. Making sure that everything worked smoothly. Also, other students who participated in the data processing, especially Charlie, Alexandro, and Nicolas, who basically spent a lot of time developing stuff for this to work. And of course, last but not least, all the sponsors who generously donated some money for helping with for this organization. I hope you had a good time. There is now lunch for you, waiting right outside, and I guess see you next year.